have, okay, from the starting, and that the beam from the top comes here, okay, and then we bend horizontally, okay, so beam come from the top, and then the magnet will bend on the surface, and this beam then goes into a different one experimental area here, then further accelerate through a superconducting DMAC, and again go into another experimental areas, okay, where this Sugam was telling now, experimental areas like HIRA, NAND, INGA, okay, so there. Now, at the moment, this facility is open for all researchers across the country, and we are getting too much applications to avail the beam time, and as a result, at the moment we are highly overloaded. Okay, means students doing PhD, they are not getting their beam time on scheduled times. Okay, so now so to just lower down the burden, okay, we build another accelerator here. Okay, so this will provide the beam to this second experimental area. So technically we can run the experiment in both the experimental areas at the same time. So one with the precision electron, other with this facility, which I'm going to show you. Other advantage of this facility is called high current. Okay, so for example, this facility which we have or existing, that produce a current of, let us say, 1 nanoampere, 2 nanoamperes. Okay, but this facility can produce current in microamperes. Okay. Means 1,000 times higher particles it can produce. So you can think like if that facility gives only, let us say, 100 particles, or let us say 1 particle, for the sake of simplicity, 1 particle per second, then this facility is going to give 1,000 particles per second. So you have a sample, and you are bombarding the particles on the sample with some particles. So that facility is giving, let us say, only 1 particle per second, then this is going to give 1,000 particles per second. Okay, so this is much higher.
And that is determining the current, the rate at which it is striking this.
That's true. And as a result, the experiments can be done faster. Okay, so the amount of time generally it takes to complete one experiment will be much faster with these facilities. So this will help us to reduce our burden, okay, and students will get their beam time on the time. Okay. So what this facility exists actually, so in this facility, so in our accelerator facility, what we have, we need ion source to produce ions, all sorts of possible ions, and then we need to accelerate them. Okay. So here we have one ion source. Okay, we call it is an ECR ion source, electron cyclotron resonance. Okay. So in this cyclotron, electrons are accelerated with the RF field or microwave field, and these electrons then going to hit the gaseous particles, and they are going to ionize it. Okay, so it can produce, let us say, argon 1 plus 2 plus 3 plus 2, argon 18 plus also. It can fully strip the argons. Okay, and then those ions which are produced inside, okay, they can be taken out. But this ion source has a facility, that it can actually produce all sorts of ion, okay, to 120 ampere. So you can see that in periodic table, up to 120 mass number, okay, you can produce all ions in this facility. So this facility can then, these ions can be taken out. So at this location, when the ions are coming out of the ion source, they have an energy of 8 keV, kilo electron volts per mass. So for example, let's oxygen. So oxygen is coming out of this source, then at this location the energy will be 8 keV into
16.
Then we have one accelerator here, that is called the RF2, radio frequency particle. Okay, so inside you have 4 rods. Okay, and this rod has small modulations which produce electric field along the axis, and these ions then pass through this and will get accelerated.
Electric field, no?
Electric field.
Okay.
On electric field. Okay. So these ions, when they come out from this accelerator, so they injecting at 8 kV per U, but when they come out, energy becomes 180 kV per U. Okay. So again mass time. Okay. So 180 into 16, let us say. Okay. Then this energy, this particle further going to accelerate through 6 accelerators. They are called DTL, drift tube linacs. Okay. So they are look like this way. So you have multiple cavities inside. Okay. So these are actually plates, gaps.
Like capacitor.
Like capacitors, exactly. So one plate is positive, other plate negative. So let us say charged particle enters. So this negative plate going to pull it. And then we have another cavity there. Okay. But when it enters the second part, then this is negative, this is positive. As you can see, the plate remains the same, it will pull back. Okay. What we do, we have to switch the polarity. Okay, this become positive, other become negative. So this is the RF. This is what the RF does here. Okay, so cycle when changes. Okay, so the plate polarity will change. Okay, and the particle always see the right electric field and keep accelerating.
This frequency is very high. It's like some.
It's 97 megahertz. Okay.
Okay.
So this frequency 97 megahertz means you can think simply 100 megahertz also. Okay. So 10 to the power 8. So the polarity changing 10 to the power 8 time in a 1 second.
And then as soon as it leaves that particular plate, it will get a repulsion also from that because now it has changed its polarity.
When the polarity changes, then it will again push forward. Okay. So for example,
पीछे की तरफ repel होंगे ना, तो it will go forward.
exactly. So they always go forward. All the time always go forward.
So as it leaves one this
That's why we
the
need
other,
superconductor here.
No, not necessarily. Superconductor only need for to just to reduce the
At
power.
that high frequency, the temperature will be too high because of resistance. Because current will move like this.
Then we have a water cooling system. Okay, so that can take care of that heat produced. So this facility we're going to see. Okay, so you have 6 cavities here, and this is going to accelerate, and then further we're going to bend it. And there's no accelerator here; it's only bending. Okay, and then it enters into the here is a superconducting linac. Okay.
Okay.
So superconducting and normal conducting, the difference is the power consumption of it.
also the thickness of the if we use copper, then the thickness of that plate required will be much larger as compared to if you have a superconducting one, isn't it?
Definitely, it has more complications also superconducting one, but technically power requirement. Okay, so power requirement becomes much less in the superconducting one. Okay, so we're going to go there and then we will see. So this finally accelerated by the superconducting one, and then going into the different experimental areas which shown by the Subirnath. Okay, NAND, Inga, Hira. Okay, so the energy will come out here. For the superconducting, energy is in the range of 200 MeV, 250 MeV, like that. Okay.
And then that beam has
That
sent
is
to
used for
other.
the different experimental areas.
And what material do you use for superconductor?
For the niobium material, that is, niobium is the material used for the
And for nuclear collision, minimum is like 15 MeV, no?
It depends now what types of ions you are colliding. So you have a let us say lighter ions, okay, then the Coulomb repulsion is much less, okay. Then low energy also can work. But when you go for the higher nucleus, then the repulsion is much higher. Then you need more. It all depends.
What is the range of order?
We start from 2 MeV to let us say 400, 500 MeV.
And we are producing 180.
It depends on different ions, no? So I'd say this is again like told you, no? This can go to 100 MeV to 300 MeV.
Per mass, per
No.
total overall, into multiplied by 16.
Niobium, it is superconduct 9.7.
9.12.
12.
Kelvin.
We produce
So we
that
have
kind
to
of a
so we have to cool down here by the liquid helium. Okay, so we have one liquid helium plant here. I hope you will see that also.